Thermodynamics. We will be examining the relationship between chemical reactions and energy. We will look at how chemical reactions exchange energy with their surroundings and how we measure the amount of energy that is being exchanged. This information is quite critical in processes such as heating our homes, as well as the production of energy for our society. We describe energy as the capacity to do work. Energy can be divided into kinetic energy and potential energy. Kinetic energy is the energy associated with motion or movement of an object. Potential energy, on the other hand, is the energy associated with position or composition. Thermal energy is one example of kinetic energy, and this is the heat that you feel from your coffee cup. And the reason it is an example of kinetic energy is because this heat is generated by the movement of particles within your coffee. Chemical energy is the energy associated with the position of electrons or molecules, and this is a form of potential energy. The law of conservation of energy. This law states that energy can neither be created nor destroyed. What we can do, however, is we can change energy from one form to the other. In this example, energy is contained in the spring that is being compressed. As the hand is removed from the spring, the potential energy that was in the spring is now transferred into kinetic energy. In order to track energy changes, we define a particular area in which we are going to be viewing these changes. For example, imagine a coffee cup in a room. We define the coffee cup that contains your hot coffee as the system. And we define the area around the system as the surroundings. In thermodynamics, we will talk about energy changes between the system and the surroundings. Units of energy. The unit of energy is defined as the joule. 1 joule is equivalent to 1 kilogram per meter square per second square. A joule is a relatively small amount of energy. 1 calorie, which is also a unit of measure, is equal to 4.184 joule. Or you can also measure energy by kilowatt hour, which is equivalent to 3.6 times 10 to the 6 joules. The first law of thermodynamics. The first law of thermodynamics is basically the law of energy conservation, which states the total energy of the universe is constant. What this means is that since energy is neither created nor destroyed, And since the universe does not exchange energy with anything else, its energy content does not change. Internal energy. We describe internal energy of a system as the sum of the kinetic energy plus the potential energy. Internal energy is what we call a state function. With a state function, the only thing that matters is the initial and the final state of the system. It does not matter how the system gets to its final conclusion. For example, if you are climbing a mountain and there are two paths as shown in this slide, one path, path A, is 12 miles long, while path B is 5 miles long. In a state function, it does not matter how you got to the top of the mountain. All that matters is that from 0 to the top is 10,000 feet. That is a state function. Like altitude, an internal energy change, delta E, is defined by or is determined by the difference in the internal energy between the final and the initial states. And so in a chemical system, delta E equals to the energy of the final state minus the energy of the initial state. In a chemical system, we can say delta E is equal to the energy of the products minus the energy of the reactants. If a system loses energy to its surroundings, then delta E of the system is negative, and delta E of the surroundings is positive. If energy is introduced to a system, then delta E of that system is positive, and delta E of the surroundings is negative. A system can exchange energy between its surroundings and itself. This is done through heat and work. According to the first law of thermodynamics, the change in internal energy of a system, delta E, is the sum of the heat transferred and the work done. Heat is the exchange of thermal energy between a system and its surrounding, caused by a temperature difference. Temperature is a measure of the thermal energy within a sample of matter. Therefore, heat is the transfer of thermal energy. Heat is directly proportional to a change in temperature, delta T. We call a system's heat capacity as the measure of the system's ability to absorb thermal energy without undergoing a large change in temperature. This heat capacity of a system, is defined as the quantity of heat required to change its temperature by 1 degree. The specific heat capacity is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Heat capacity can be used to calculate the heat in a system. Heat is given by the equation m, which represents the mass of the substance, multiplied by the specific heat capacity by the change in temperature, delta T. This temperature is measured in Celsius.